Okay, well, good afternoon, everyone. My name is Mortaza, and I am the training coordinator for the Australian Space Data Analysis Facility. Thank you for taking the time to attend this event today. I would like to begin by acknowledging the traditional custodians of the land on which we are located and pay my respects to their elders, past, present, and emerging. If you're not familiar with ASDAF, ASDAF has been established to assist Australian SMEs and researchers in improving their capabilities to capture and use space data, in particular Earth observation data. ASDAF aims to increase the likelihood of commercialization success in a wide array of industries by connecting and leveraging existing national and state-based computing and data resources. We offer services such as access to Earth observation data, specialized data analytics expertise, training and workshops, and knowledge sharing and collaboration opportunities. Today we've got a very exciting talk. I would like to introduce our speaker, Dr. Tino Heimhuber. Tino is a postdoctoral researcher at the University of New South Wales Water Research Laboratory, specializing on the application of advanced computational methods, remote sensing, and geospatial analysis for holistic river, wetlands, and estuary management at the system scale. Tino's current research focuses on coastal zone remote sensing and the economics and engineering methods around the blue carbon ecosystem restoration. Thank you very much for your time today, Tino. Over to you.
Sure. Thank you very much for the introduction. So I am just going to share my screen here. So please let me know if that is working. Oh no, that's the wrong one.
Perfect.
Oh, you're looking at the top slide, yeah?
Yeah.
Cool. So yeah, thanks for the introduction, and thank you all for joining me here on this presentation. I hope, I'm sure you all afternoon, the exciting as possible, which usually isn't all that hard with cool satellite data. So maybe quick background on myself. So I'm originally from this place here that you can see from, so just checking, you're seeing the slide deck, Mortaza?
Yep, I can see the slide.
Cool, not the globe, okay. This is a place in southern Germany on the border to Austria. That's where I grew up, and so on. It's a very different setting from here over in Australia, where I live now. I had the pleasure to do a bachelor and master's in environmental engineering at the Technical Uni in Munich, where I specialize on GIS methods in hydrology, which got me really excited sort of into this space. And then in 2014, I came over to Sydney to do a PhD at UNSW on large-scale surface water dynamics across the Murray-Darling Basin, using satellites as well. And then I landed a postdoc at the Water Research Laboratory, which is a really cool place because it's a mix. So we have 50% consultants that do applied coastal engineering projects, and 50% academics. We're doing teaching and research, and there's a lot of sort of collaboration between the two groups. There's a lot of exciting stuff usually happening. I thought before I jump into the InletTracker tool, which is the focus of today's talk, I'll do a really quick run through some of the fundamentals of remote sensing that are relevant here, because just to make sure we're all on the same page. So those of you who are remote sensors, just please bear with me. And this guy here that we're looking at is actually my great-great-great-grandfather, who used to be, or who was, one of the first photographers in our region. And I kind of like to think that remote sensing runs in the family a little bit, because if you think about it, remote sensing, or the study of an object from the distance, really kind of began with the advent of photography. It's really all we're doing, or both kind of tasks. You're going to be using the visible or electromagnetic radiation, typically the visible range, to infer information about stuff from the distance, right? And it's really important whenever we do remote sensing to have a good physical understanding of electromagnetic radiation.
Apologies, Tino.
Yep.
Sorry, your slide is not changing at my end.
Oh, so you're still looking at this globe.
At the
Oh, sorry. So yeah, that's why I
the
was
top
asking.
screen.
Sorry.
Yeah.
That probably
Yeah.
didn't make sense at all what I was talking about. So I'll share the. Maybe I need to just share the screen. How's this now?
Yeah, perfect.
Yeah, better. So just for reference, because nothing would have made sense to you if you wouldn't have seen this. This is my hometown. This is the Technical Uni of Munich. This is the Water Research Lab, and that's my great-great-grandfather. So sorry about that. That's why I was hesitating, because I kind of saw the other screen being shared. I'm a bit new to the Cisco software. So anyways, here we're looking at the electromagnetic radiation spectrum of different wavelengths, and we can see that particular for the visible light. And in microwaves, you have a very good transmissibility in the atmosphere. So it's very useful to work in these wavelengths. So that's typically what the majority of sort of Earth observation satellites are using. And then we just usually take this information through a lens. It then goes on a sensor, these little arrays that transform the electromagnetic radiation into digital value for each of these little grid cells. And then we store that in a digital format like a JPEG, or, you know, if you're a photographer, you're familiar with raw images, where you just have for each pixel a lot more information stored in terms of the brightness value. And if you overlay different of these spectral bands, you can get stuff like a normal color image or other interesting combinations. You can also do hyperspectral imaging, where you're essentially sampling the whole spectrum by using hundreds or thousands of little sort of snapshots along the electromagnetic spectrum. And then if you think about an Earth observation satellite, you're looking at, you know, large areas, and typically you then, for each pixel, you're looking at different stuff, right? Like vegetation, water bodies, sand, etc. And all of them have very different, what we call spectral signatures. You can see some of them here. And that's then where we can infer information about the land surface or changes therein. And so just as an example here, these are different types of water bodies on a Landsat satellite imagery. And you can see they all have a similar shape of the spectrum, but they all have these sort of nuances. And this is typically what we do to dig deeper at what we're actually looking at. And just in terms of the data that also InletTracker is using, whenever you do sort of long-term change analysis at the land surface, you're hardly ever going to go past Landsat, because that's just a satellite or suite of satellites that's been around pretty much the longest. So since about the mid-80s, you get really high quality sort of 30-meter pixel imagery. And again, the parts of the spectrum that they're sampling, you know, in addition to the red, green, and blue, they're typically aligned with where the atmosphere lets through a lot of this radiation. So the near infrared and then the shortwave infrared bands, which are particularly important when you're trying to look at water bodies from space. And just to wrap this up, there's nowadays, since maybe 5 years, there's this Sentinel suite of satellites, which are also, the data is free to use for everyone. And these are from the European Space Agency, and they really stepped up the game one more step in terms of higher resolution, both in space and time, which is fantastic data to work with. And of course, most of you probably by now heard of these CubeSats as well, which, you know, they just work in these constellations, pretty much a chain of small CubeSats that are looking at a narrow band of the Earth. But because there's so many of them, you can pretty much get a picture of the global land surface every day, or sometimes multiple times a day, which is also at about 3 to 5 meter resolution. So that's enough, I guess, for an introduction. Let's jump into the actual tool. And just so you have a bit of an understanding how this came about. So Kilian Voss is a colleague of mine, and he's a PhD student. he developed COSAT, which is also a satellite remote sensing tool that looks at, as you can see on the images to the left here, it looks at the location of the beach or shorelines, you might say, the interface of the beach with the ocean, and tracks that over time. And so he just came to me because he knew I was working a lot in estuaries and lagoons, and he said, look, the tool's definitely picking this up, but he wasn't interested in it. Like you can see the lagoon here to the north, you can certainly see times of when it was open and closed. And basically what he did, he sent me down this massive rabbit hole, because that was about 3 years ago, and I was really intrigued by this problem or this potential. And so I went into it, developed this tool over multiple years, and eventually was able to sort of crack it and publish it and develop it to its full potential. And so you might wonder now why we actually care about these kind of coastal systems that the tool is tracking. So in Australia, we call them intermittently closed and open lakes or lagoons, or ICOLLs. And those are really just any coastal lagoon that is sometimes connected to the ocean, and at other times it's just disconnected, like on this example. And it just happens to be that in Australia, we have a large chunk of the global pool of these systems. So there are about maybe 2,000 across the world, and 33% or so of them are in Australia. And they often tend to be places where we like to, build cities or campgrounds, or just hang out for recreational purposes. So there's actually usually a very high ecological value and a high socio-economic value associated with them. And over here, you can see a water level sort of dynamic in one of these systems over several months. And you can see when they're open, they're obviously tidal. So you get this daily fluctuation, and when they close, they don't fluctuate, but the water level just gradually increases or decreases with rainfall and evapotranspiration until it reaches a point where it's high enough to breach the beach berm and sort of flood out into the ocean, and then becomes tidal again. And the point is that for many of these systems, these data sets just don't exist. So we have a very poor understanding of how often they open, how often they're closed. And this is often very important information for the council. And so having this information in the satellite data available for free was, really a game changer in this context. And so I just set out and did some initial testing, right? That's always what you do first. And you can see one of these systems here, Naji Lake on the New South Wales coast. And you can see a spectral transect extracted on the green line plotted here at the bottom. And you can see that when it's open, you can clearly see a signal here in this index, which is the normalized difference water index, or NDWI. And this index just basically amplifies the presence of water over all other classes. And so you can see that there's clearly a signal in the data that we can make use of. So that was promising. However, I also quickly realized that it's a very challenging application of remote sensing, because if you look at the typical pixel size here of a Landsat image and the size of some of these ICOLLs or coastal inlets, you can see that they're often small, relatively small landscape features that we're trying to test here. So, the channel might be actually just half the width of a pixel, which is problematic, because then you get these mixed pixels. Or you often have these steep headlands that can cast a shadow, which you can imagine changes, again, the spectral signature dramatically in these locations. But I didn't give up still, and I thought, well, what if for each image we can sort of automatically identify a connection between a point in the open ocean and inside the inlet, right through that water channel? Because then if we extract that transect, we should be able to sort of see a class separation, right? The ones that have water underneath should look much different than the ones that have to go over a beach berm. The question was just, how do we get this transect when the inlet is moving all the time, because it's a dynamic coastal setting? So again, I didn't know how to get there, but you could just clearly see it on these images that it's got to be possible, right? And so I just thought about this problem of almost having to go from a point A to B in a hilly landscape like this one on the photo. But instead of going the shortest connection, you sort of wanted to go along a path of least resistance, right? Where you have to sort of accumulate the least amount of elevation gain over your path, because that would probably mean that you're going through that deeper water inlet channel. So I did a bit of a digging online, and I came across this least cost pathfinding algorithm, which is often used in, say, a navigation system when they tell you the fastest route from point A to B in your car, for example. And so basically what I did was I took this water sensitive image index as a cost raster, and basically a raster can be transformed into a grid of points with line connections. And then we just let the algorithm route through that cost raster and identify the cheapest or least cost path, right? Like you can see on this animation to the right here. So that was cool. So I tried that, and it was very promising. But I also quickly found that, you know, I could set up these points, sort of, we call them seed and receiver points for the algorithm. But unfortunately, I found that quite often it would try to shortcut over the berm, over the beach still, instead of going the longer distance, because the cumulative cost was still cheaper. And luckily, there was a fix for that, which was to just amplify or exaggerate the cost surface. So make the highs higher and the lows lower, like on the right image here. And after doing that, pretty much the algorithm started doing exactly what we wanted it to do. So the case was kind of solved at that point. Just to give you a bit of a feel how that looks in practice. This is Darras Lake, also on the New South Wales East Coast. And you can see that pretty much for every image, we get a perfect, like almost better than you could do it with the human eye. We get a perfect tracing of the channel without, you know, any kind of manual step involved. So that was really exciting, getting to this point. But of course, we wanted to take it one step further, which was, can the algorithm actually also automatically tell a manager if the system was open or closed at a particular point in time or image? And so you can imagine if you do this, so often these Landsat series, you get 1,000 images over 30 years. And so that kind of then gives us 1,000 of these transects, right? And you can see that clearly there's a separation there. The ones that are open, they just have this dip. When you go from along the beach, you sort of go from sand through the channel, through the back to sand. So you see this dip here on the C to D transect. And so what I did, I simply said, look, on an open image, we can just use, sort of identify this threshold, which is the value, sort of spectral signature of sand, and look how much do we deviate from that at the deepest part of the channel, which we automatically inferred, right? So sort of this distance here from that bottom point to the baseline, that's an indicator of the state of the inlet. Because if it's closed, it will look like this, and it will be 0, because it's just sand across the entire sort of C to D transect, right? And so that was cool. And so that's basically then how InletTracker was born. Here you can see sort of a high level overview of that. So you know, you have satellite collecting imagery where that is collected by NASA, USGS, and the ESA on their base stations. It goes to Google Earth Engine, and that's where we actually download the data from automatically. And we then do a whole bunch of image processing, and you get a useful information spit out by the tool at the end. And as I said earlier, you can sort of start the analysis around 1985, obviously up until now. And especially in the last 5 years, we get Sentinel-2 and Landsat 8. And so you get a very high sort of revisit frequency. So pretty much you get an image every 5 days, which is really useful for some of these sites. In earlier days, you sort of get an image every 16 days to several months if there were clouds around. So this was just recently, is pretty fresh, everything. This was just recently published in Geomorphology. And you can, if you're really interested in digging deeper with the tool, there's all the sort of validation and calibration is presented there. I won't dwell on that for too much. But I'll show you just some of the results that you can get here for these 3 example sites. So again, there are 3 coastal inlets from larger to smaller. And essentially, I know there's a lot to digest here, but basically these points, these values, they're what the tool gives us. That's that parameter, like a deviation from the baseline. So whenever it's high, we suspect it's open. And then the blue and the red dots means that an analyst or a student of mine looked at the image and said, yeah, that's open, that's closed, that's open, that's closed. And then the gray boxes says that the council record, sometimes they keep a record, states that it was in fact open. And the green one is just a tidal range. And so you can see in this case, there's almost a perfect agreement across these, the satellite data, as well as 3 independent validation data sets, which was again very exciting because we never thought at the beginning that we could get to this level of detail. And pretty much the same for the other sites. Just there was a lack or gap in the council record here. And you can see even this coiler, which only opens for short periods of time, like several weeks, we still captured the majority of these shorter openings, which is important because you might obviously miss them if there wasn't a satellite image captured. So that was very promising. If you zoom in, this is just the same data, but for only the Sentinel-2 sort of record. Again, very clear-cut signal, satellite, and the InletTracker tool is doing its job just fine. One thing that what was interesting was that if you can imagine you have an open inlet, that will look very different if it's a very high tide or very low tide when the image was taken. And that's exactly what you're looking at here. So this is a low tide image to the left and a high tide image to the right, and they're just 5 days apart. And so for that reason, we actually integrated a global tide model into the tool. So when you set your site, the tool will automatically drill into that global tide model and extract the most likely tide level at the time the image was taken. So these white dots are images, and you can see that you get images during high tide, during low tide, and pretty much everything in between. And that's useful information again for you to sort of make a judgment call as to how big is the inlet, how deep is it, and so on. And then that was just a starting point, but obviously you can apply this tool in many, many different settings. So for example, I thought this was an interesting case study here, so I'm just showing it to you. The Rio Grande river mouth, that's a river that's on the border between the US and Mexico and drains into the Gulf of Mexico over here. And I read in a book that because of drought and too much water extraction upstream, the river mouth dried out completely in around 2001 for the first time since records. And so I just thought, well, let's run the tool and see if this is correct. And in fact, that's exactly what the tool said. So you can see it's just always open. And then we had the big drought and maybe compounded by too much water extraction, and the river mouth completely dried up for almost a year and a half. And you can also look at stuff like barrier breaches that you get sort of on these fringing sandy islands on the east coast of the US. You can see there isn't a connection until a hurricane comes and breaches an inlet through those islands. And you can clearly see that signal in the satellite data as well. And then just to give you an idea of sort of where we're taking this experiment next, obviously this is a game changer for ICOLLs, for these systems. And so we're now running this for many, many systems around Australia, but also around the world, to see if we can actually use these systems as sort of sentinels for, say, changes in climate. So if you imagine a declining rainfall trend, that would mean that these systems open less And so we should be able to see this in the satellite data, and that's just sort of some research that we're working on now, and it looks quite promising. So typically you can see stuff like prolonged droughts. You just don't get an opening for several years at a time. And just so a couple of remarks on also what's up next. So I'll show you a couple of animations after this, but just before we get there, this was developed from the get-go as a community tool. So it's all open source code on GitHub. I'll show you in a minute where this can be accessed. And we just sort of try to set a baseline that makes it really easy for people to run these kind of analysis, whether that's a coastal system or inland, doesn't matter. But we're hoping to see researchers from around the globe or practitioners to pick it up because it's quite easy to use, and just add maybe coding functionality to it and just develop it further. So that's sort of the whole idea. And like I said, we're working on a large global scale experiment of these ICOLL sites. And I'm also trying to put up these Water from Space weekly animations on social media, where every week pretty much we're looking at a different site, and you can see the animation and maybe what's been happening there over the last sort of 30 years. So, and like Mortaza said, please jump in with any questions, but in the meantime, I'll just show some of the tool in action. So Mortaza, please tell me if in a minute we're looking at these the globe here.
Yeah.
Yep. Cool. So now I just need to get started. So what we're looking at now is 3 examples of InletTracker in action. And the first one is, some of you might actually know it, it's the Manning River, just about 4 hours north of Sydney. And that has two river mouth, so to speak. And one of them is actually intermittent. And it gives managers all sorts of pains. They have to dredge it to keep it open. And when it's closed for too long, there's a lot of community pressure to open up again because you get problems in water quality and so on. So again, we're going back here 30 something years in time. And you can see it's a fairly large system, so that beach berm is almost from point C to D, that's almost, I think, 2 kilometers or 2.5 kilometers. And just before you get overly confused, I'll just run you through what you're actually looking at. So on top left, this is just a sequence of the satellite imagery, and L5 just means Landsat 5, and you can see the date here, 1990. At the bottom, you can see the transects of the spectral index from point A to B, so through the inlet or across the berm, and then C to D along the beach pretty much. That's when you get this high value dipping through the channel and then high value again. And on top here, these point plots are just, again, that deviation from that baseline level. So whenever that's high, we're thinking we're looking at an open inlet. And the cool thing here is that you just see how much that's moving around. It's just quite fascinating due to these various interacting coastal processes. You have the wave action, you have sometimes floods coming down the river, or you can have just the tide going in and out of the system, literally, carving away at the channel, sort of almost creating this meandering effect that we sometimes see in a river channel. You can see, for the first time they're closing briefly in 2002, and then opening again at a completely different location. And then it's slowly working its way sometimes down the beach berm again. So it's really quite, to me, it's always fascinating to see these 30-something years of coastal morphology, unwinding and sort of bringing them to life through the satellite data. And it's pretty much for every site that I'm animated, there's always been a lot of interest actually from. So this is this just gives you the perspective. This is the same location when it was closed, right? And you can see, you might imagine how that creates a bunch of problems. You get sometimes high nutrient loads into these waters and lack of oxygen, and the water gets brown full of natural tannins, and often the community doesn't like that, even though that's quite a natural state of the system. What we're also going to see shortly is that this year we had a major flood on the East Coast, and that really blasted the inlet open in 2021, and we get a massive channel then at the very end. So it was closed actually, like shown on the image there. And then here you can see we had a massive flood in the Manning River. You may have seen the images of houses being washed down the river or across the floodplain, and that obviously washes away a lot of that sand that's accumulated inside the inlet out through the ocean, just because of these large high flow velocities, high volumes of water coming down, and you can see it here as well, just a very big pronounced channel. And all of that pretty much we can see from space, which I thought was really cool. Here's another example. That's Lake Illawarra, about an hour and a half south of Sydney. And that's also interesting because that used to be a natural intermittent system that sometimes closed off. It will certainly often go through periods where there was a lot of sand accumulated in the inlet here. You can see that here. And the community really didn't like that. They really wanted clear turquoise oceanic water for most of the time. They didn't like these brown water periods at all. And eventually, council and so on, or a decision was made to train, what we call train the entrance. And so infrastructure was put in place. Training walls, so there's just rock walls along the edge of the inlet that sort of guide the flows in a particular channel, a particular direction. And when you do that, you typically create enough scour to keep that permanently open. And then this was complemented by literal, training walls here and here eventually. And if you watch carefully, you can see just how that system was just put in place, was fixated, and over time the tides would just scour out the channel bigger and bigger and bigger. Sorry, that was a bit too fast there. And at the end, eventually, actually that scour got so significant that the bridge across the inlet further upstream from point B here, the pillars of the bridge actually got scoured out, and I think they're at the moment, or if not, have already renovated that for a lot of money. So it's an interesting site because it was a planned intervention, but it has caused some headaches down the road now. But again, all this we were able to observe just purely from space without ever actually visiting the site, which was cool. And then lastly, there may be some people here more interested in inlet waters or wetlands. And that is certainly something that you can also do with the tool. It's just because you're looking at shallow water environments. So this is a case study here near Melbourne, where they have these decommissioned salt ponds. So they used to be used for salt production up until a couple of years ago. And now they just ceased production, and they actually handed or sold them to Parks Victoria. And they just sort of want to know what to do with them. And it turns out that it also used to be very important bird habitat, these sort of ponds, because even in summer when there wasn't a lot of these kind of shallow water environments around, they could go there for foraging and breeding. But what we found is actually that if we look at the sort of inundation dynamics, so in this case, we're not actually doing the pathfinding, we're just looking at what's sort of the average water level inside these ponds. And you can see it just sort of seems to go through this zigzag motion. If you look at the time axis here, that's pretty much just a seasonal signal. So every time in winter, when rainfall significantly exceeds evaporation, you get these ponds filling up just naturally. And then in summer, they tend to sort of dry out. And that is interesting because in summer is when these migratory shorebirds actually used to use the site the most. But however, now we're proven here through the tool that there isn't actually any water there in summer for most of the time. So that habitat value has been actually lost when they stop pumping for salt production. And again, this was useful because we had obviously conceptualized that because it makes sense, but this was just, you know, pretty solid proof that that is indeed the case. So again, satellite data providing really invaluable information here. And so just one last thing here that I wanted to share with you is if anyone's actually interested in using this tool, you can just Google InletTracker and you'll quickly should be able to find the GitHub page. And that's really where the entire, so it's essentially, it's just a suite of Python codes, right? And I put a lot of time into making them, organize them very well and structure it. And then there's a whole long list of how to actually get the tool set up. You know, what does it do? Step by step, you know, how do you set up that Python environment on your computer? We use Anaconda here, which many of you probably are familiar with. And it really, usually now when I do it on a new machine, it takes me about a couple hours to set it up. And once you set it up, you just go, you load a shapefile into a QGIS or whatever GIS software you're using, and you can set up a new site in 5 minutes. So all you need to do is just set these points in the GIS file, save it, and then the Python code will just query that GIS file based on the name of the site, and it will run the whole analysis for you. And you get outputs automatically, such as these transects and so on and so forth. So yeah, if you're interested, I'm always happy to help you with that setup. And you can see there's people are slowly starting to use them. They're forking it. They're adding functionality to it, and we'd like to see just more of that. And there's obviously going to be a bit of a discussion group here as well to help out with that. Yeah, and that basically concludes my talk for today. And feel happy to take any questions.
Thank you so much for that, Tino. This is clearly a very powerful tool, especially given the significance of coastal inlets. So if anyone has any questions, please feel free to use the chat section. We've got a question from Jonathan. Does your code also download the imagery automatically?
Yes, absolutely. So basically, when you install that Python environment, part of that is installing the Google Earth Engine API. And that is essentially a connection between your computer and Google Earth Engine. And so just from that, setting up that shapefile in QGIS, you can automatically download all the Landsat 5, 7, 8, and Sentinel-2 imagery. And it's going to project them all into the same projection, and it's going to resample them all to the same resolution. And so, yeah, that's all happening. It's downloading the imagery actually to a specified drive or your local hard drive. Because we're looking at small systems, it's actually, and we're not downloading the whole Landsat team, we're just downloading a bounding box. And so usually you end up with maybe 0.5 gigabyte or 1 gigabyte of data for one of these sites. So it's, yeah, absolutely. That's all happening in one click of a button.
Okay, I've got a question for you, Tino. Sure. So InletTracker is developed to be used for monitoring coastal inlets. Mm-hmm. Are there any other applications for this tool, or have you heard from people who have been using it for other purposes?
Yes, I think the second biggest one is probably, and I'm probably going to call it wetland tracker, is there are, I mean, for wetlands, again, this long-term satellite data is a game changer. Previously, you'd either have to have a logger in there or have some set of aerial photos, or maybe you have a hydrodynamic model. But now, if you think of these inland wetlands in the Mare-Darling Basin or Kawanga Delta in Africa, now we have 30 years of surface water extent dynamics, right, from the satellite imagery. And that's just so useful for better understanding just the hydro period, like how often are these wetlands inundated? Is there seasonality to it? Are there extreme events? All these sort of things that we can link back to hydrology or flooding and so on. So wetlands is a huge one. You know, the scientific community around wetlands is hopefully going to pick this up. And the other thing is pretty much anything, yeah, like inland rivers, I would say. We often have these, some rivers are quite static, but other rivers that have these meandering dynamics, if you can imagine. I mean, you could perfectly trace that location of the meandering river channel over time. And the cool thing, there's other tools that do this, remote sensing tools, but here you'll actually get the deepest path in a river, right? Which is often coincides with the navigation channel or a dredging channel. So that's very useful. And like I said, pretty much on a monthly basis, I get an email from one of our project engineers. They put up a new proposal for some sort of coast engineering project, and they're like, hey, could we just add in the tracker to the proposal? Because the client wants to understand, you know, the long-term dynamics of the site. And so, yeah, those are probably the big ones: rivers, wetlands. You can get creative. You can obviously look at vegetation or other stuff, but these are the big ones.
Okay. We don't have any questions in the chat section,
Cool.
but I think, okay, so we've got another question from Jeff. Have you thought about extending to multispectral sensors or to try to extract inlet depth, for example? Depth?
Yeah, those are fantastic questions. So the first question, we haven't looked at multispectral data because, yeah, part of the, I guess the main goal usually when looking at inlet is just getting long-term information. And to the best of my knowledge, there isn't a lot of, I mean, this is actually multispectral imagery, right? The Landsat data. It's maybe, what, 8 bands or something. But we haven't looked into hyperspectral imagery just because there isn't that good enough amount or coverage of this data. I know there are some newer satellites that provide this data, but it's not as easily accessible as, say, these long-term workhorses like Landsat and Sentinel-2. But of course, one thing that they've done for COSAT, they've looked at the CubeSat imagery. Because that's daily and 3-meter resolution, that obviously provides really good, promising data for sort of, you know, near real-time monitoring. And the depth of the water, that is something that I've always considered, but I haven't yet. So we know satellite-derived bathymetry, it's absolutely a thing, but it is also very, very difficult from a physical point of view. Because on each of these images, you have a little bit of a different sun angle. You might have ripples on the surface of the water, and you have different suspended sediment characteristics in the water as well. And each of these factors influence how water depth relates to spectral signature. And so you can do it, but it just, there's so many competing factors that you have to develop really complex kind of model. Obviously, this data that we're getting here, it's, I would say it's proportional to the depth. It's just not, you know, accurate to 10 centimeters or so. You can see this was deeper than the next image. We just can't say I was exactly 1 meter deep. That's just, yeah, it's just complex. But if anyone wants to add that functionality to the code, I would love to see that.
Okay. We've got another question from Jonathan. Any comment regarding SAR?
Yeah, similar answer. So SAR satellite, is it satellite aperture radar? So anyways, it's microwave remote sensing, right? And so these are very different satellites. They emit microwaves, and then the microwave bounce off the land surface, and then they record the signal that bounces back. And so when you have a water body, it just bounces off like on a pool table, like a ball on a pool table in the opposite direction because it's a smooth surface. And so water bodies are dark. Vegetation is very bright because it sort of bounces back in the same angle. So you can clearly map surface water on these SAR imagery. And the cool thing is you can look through the clouds. So clouds are not an issue. But again, it's just, I worked with SAR data a lot in the past, and it's just not that easy to work with. There's a number of pre-processing steps to get to actually an image that that looks quite, normal for us to work with. And I know Google Earth Engine has some of this pre-processed imagery, but at this stage, it doesn't. The tool doesn't integrate this data set. It would be useful. I don't know how much actually you would be able to distinguish between flat sand and water. I haven't done this test. You probably will be, but at this stage, we just sort of try to balance, the complexity and what we're trying to actually get out of here. And so we just went with the easiest, most commonly available data.
Okay, so I'll go. We've got another audience question, and then
Sure.
I have a question at the end. Have many management decisions been made using your tool?
So that's, a great question. Yes and no. I mean, I really only cracked the problem earlier this year. And so like you saw, I think on the GitHub went live in April or so. And it has been used in several projects, and I would assume that they have derived some sort of decisions from that. But I'm hoping this is just, fresh out of the oven, and it is being used. And so I'm hoping that this is increasingly going to be the case. And again, it's probably not your holy grail data, but it's very good to complement any field measurements, because you don't want to go out to the site every week and do a survey. That's going to be very costly. But on the other hand, like, I don't know how it's over. You have some of these systems in Western Australia as well. And for the council, they're just very painful to manage, because you have this community pressure, you have this crazy climate variability that we have all around Australia, and you have water quality problems, you have coastal, it's complex. And so it has really helped to just provide evidence, so we can actually do evidence-based decision making. I think that's kind of the game-changing aspect of it.
Okay, as a final closing question, I know that this tool extracts or gets its imagery from Earth Engine. Is it possible to use imagery from other sources, for example, Digital Earth Australia or any other sources?
Yeah, that's another great question. I mean, I guess we went the Google Earth Engine route because they have the global archive, so all continents. As far as I'm aware, the Digital Earth Australia, so that's Geoscience Australia, right? They have probably the better image pre-processing because it's tailored to the Australian continent. So I'd love to see that sort of bridge. But so it would be great to use this imagery for Australia, but I haven't built that connection. But it certainly could. All that we're doing, we're just downloading imagery, we're downloading TIFF files. We're just resampling them to a common resolution and projection. So it doesn't matter where you get that imagery from, as long as in that same format, it will then just plug into the tool at that stage, and then all the rest will be the same. And again, it's all open source code, and hopefully, I think it's quite nice set of code, and that most of that credit should go to Kilian. Actually, he's a really good programmer.
Okay. Well, thank you so much again, Tino, for taking the time to present here in ASDAF today. Also, thank you very much to everyone who attended online. We really appreciate your continuous support and engagement. We have some more great events coming up, so please keep an eye out on our social media accounts. Just simply search ASDAF Space. But that's it for now. Thanks, everyone, and see you guys in the next one.
Thanks, everyone. Thanks, Mortasa, for organizing. It was really cool.
Okay.
And everyone, if you have questions, always feel free to get in touch with me regarding the tool.
Okay. All right. Thank you very much. Cheers. Bye.
Cheers. Bye.